Good morning, guys. Today we'll be starting with the rest of portion, and today with this video we'll be finishing off this chapter. Okay, and I think you would have attended the live class also. During the live class, as you have seen, we have charted the new chapter. Okay, so this rest of the topic from the previous or the chapter or this chapter called Magnetism and Matter is what we have discussed about diamagnetic substance in detail and paramagnetic. Now we'll go for the last section, that is ferromagnetic substance. Ferromagnetic substance. I'm not writing the okay. Ferromagnetic substance. Now it is quite similar to paramagnetic substance. What? There is atomic dipoles and they exist, right? Just like in the case of paramagnetic substance. But the difference comes that, see, initially in paramagnetic substance, when it was kept as it is, right, the dipoles were arranged in random position, remember, right, and you gave an external field and these dipoles got a particular direction, hence they got magnetized. This is what a paramagnetic substance was. But in the case of ferromagnetism, the atomic dipoles interact with each other in such a way that they spontaneously align in the same direction, that is in small volumes. That is, the arrangement isn't just like packets. Suppose this is my a ferromagnetic substance. The dipoles will be forming, let's say, like these packets. Some of them, in this one packet, all the dipoles are in one direction. In this packet, all the dipoles are in this direction, like that. And say this packet is having the dipoles in this direction, and this section dipoles are in this direction, right? So this packet's arrangement is known as domains. Each packets, these are called domains. This you would have learned in chemistry, I believe, right? This phenomenon of arrangement of this packets or domain formation is known as ferromagnetism. Now what happens, see, when you take this section, when there is no magnetic field aligned, so this dipoles and this domain, or this domain and this domain cancel out, and this domain and this domain cancel out, right? So in a particular volume, the domain formation, due to the domain formation, the ferromagnetism doesn't have any magnetism property. But what happens when you give a magnetic field, external magnetic field, right? So when you apply an external magnetic field, the domains along, see, this direction, right? So these domains are in the same direction as that of the applied magnetic field, right? So those domains which are in the same direction as that of the magnetic field will become large, right? So first of all, we have increased the magnetic field only in a slight way. So this, suppose I'm going to draw the figure again, guys, right? This section quite becomes large. Right, this and this portion remains quite same itself. These three. I have just slightly increased the magnetic field, guys. So this three. So this is B external. Right, now I'm going to increase the magnetic field, external magnetic field further, means more dipole will have, see, this one down will have a slight bend initially itself when you are providing a little bit of external magnetic field. When you increase the magnetic field, this, suppose this packets, all the dipoles will be having a tendency, first it was bending in this way, then it increased, and then all of them get arranged in this way, right? At particular external magnetic becomes so high that all the magnetic field or all the dipoles in the domains will be having the same direction of the external magnetic field. So all the packets, right, will have magnetic field in this direction. Either all the packets or all the packets will be fusing to form one packet, like that. Then later on it might be one domain. It depends upon the material, right? So domains, dipoles, all will be arranged to the external magnetic field. This is the difference between the ferromagnetic and paramagnetic objects. Clear? And these ferromagnetic objects are strongly attracted in the external magnetic field due to this domain formation. Right, iron, cobalt, nickel are some of the example. Now next section is what is the value of what chi? Right, susceptibility. It is found that its value is positive and very large value, guys. It is quite close to 1000. right? Similarly, what is the value of mu r? That is permeability is 1 plus chi, right? And that means 1 plus 1000 is quite similar to 1000 itself. So it is also very large, positive and large value, right? Now what happens if I keep a ferromagnetic substance in a non-uniform magnetic field? So they obviously, just like paramagnetic substance, it moves from a weak field to stronger field, right? Similarly, the last point which we have to discuss, last or second last, I can say, what is a magnetic field lines? Just is quite same like that of paramagnetic, just the magnetic field lines as it attracts, right? So rather than more than paramagnetic objects, the magnetic field lines are very, very close inside. Clear? This is a magnetic field lines or nature when it comes close to a ferromagnetic substance. Now what happens? Now the extra point which we have to distance is, or what happens when the external magnetic field is removed. Right. Some of the ferromagnetic field or substances will still retain the magnetism. Right. Those type of magnetic objects or ferromagnetic substances are known as hard ferromagnetic objects. Whereas some of them, once the magnetic field is removed, it goes back to its initial nature, that is, it loses its magnetism. Those type of objects are known as soft ferromagnetic objects. So hard retains, soft loses. Right, and the soft ferromagnetic objects becomes the temporary magnets and hard becomes what? Permanent magnets. Clear? Right, now we have to move on to the next section. What happens with the nature of temperature? Right, temperature. Right, when temperature is increased, right, temperature increase means random motion of the domains of the dipoles, right? That means the ferromagnetism decreases. Right, at some point the ferromagnetism decreases means the next stage of, or the least any, or the material which is lesser magnetism than ferro is what? Paramagnetic, right? So when the temperature increases, random motion increases, ferromagnetism decreases and object starts to become what? Para. Right, so this is actually a transition phase, right, or phase transition. So ferro has a tendency to become para when you what? Increase the temperature. Right, clear? So similarly you can bring the para to ferro also, right? So some object has a tendency to have both the nature of ferro and para depending upon the temperature. This temperature where it can exist, or an object is having a tendency to have both transition from ferro to para, is known as Curie's temperature. Curie's temperature, TC. Clear? Now after TC, the material becomes para, right? After the temperature has increased further and it has reached Curie's temperature, means ferro property has decreased and becomes a paramagnetic substance. Right? Now this now ferro has completely become para, right? Now if I increase the temperature further, what will the para become? Obviously it will become what? Dia. Right? Dia means now it is totally not a magnetic object. Right? I hope this much is clear. So I can say the susceptibility is decreasing going on, right? So susceptibility is inversely proportional to temperature, right? When temperature increases, susceptibility decreases, right? So it's just like the Curie's law. I hope you remember the previous video. So an equation is related between, write down the equation guys, T minus TC, right? Where see, when T increases, T minus TC also what? Increases. Right, TC is a constant value. Say TC is 4 degree. I'm just giving an example. It's constant. When T increases, first suppose T was 50, 50 minus 4 is 46. Then again I'm increasing to 51, it becomes 47, right? So when temperature is increased, denominator goes on increasing. Denominator goes on increasing means chi's value is going on decreasing, right? So we can say that as the Curie's law stating, when T increases, chi decreases or susceptibility decreases. So it's a formula which is relating chi and temperature in the case of a diamagnetic ferromagnetic objects. Please write it down, guys. Right, now after this we have to go for a main section. I am pushing it the video because we have to go through the entire derivation of hysteresis law, and it's a lengthier section also. So I hope you remember this equation also, C mu 0 by T, right, where C is Curie's constant. I hope you remember that C. So this equation and this equation are quite similar. C mu 0, there is a mu 0, okay. So chi is inversely proportional to temperature. Here also chi is inversely proportional to temperature itself. So this is Curie's law. It's quite similar. So this is the case with the case of paramagnetic. This is with ferro. Right. So let's move on with the topic called hysteresis law. Now guys, hysteresis loop is actually, as per the NCERT textbook, it is a graph which is plotted between B and H. Right, but actually hysteresis loop is a graph which is plotted between I and H. Both the graphs are similar, but it is actually between I and H. Right, so we'll talk about it using I and H graph. Then I will tell you how it comes with the case of B and H also. And hysteresis loop, if you want the spelling, it is hysteresis loop. Loop means, I hope you understand, starting and ending comes in what point itself. Now hysteresis loop between I and H is usually for only what? Ferromagnetic objects, not for para or dia. Clear? So first of all, we are plotting between magnetization vector and magnetic intensity. Magnetization vector and magnetic intensity. Right. Now let's move on. Suppose we had an unmagnetized ferromagnetic substance and it is kept in a solenoid, and that solenoid, suppose this is a solenoid, I have not provided any current to the solenoid. So current is 0. Let's say current is 0. When current is 0, obviously there is no magnetic field, so a magnetic field is 0. When there is no magnetic field, so intensity, H is also 0, right? Intensity of the magnetic field also will be 0. When intensity of magnetic field is 0, I is proportional to H, right? So magnetization of that object which is kept inside the solenoid is also 0, right? So let's mark that point as O, where I and H both are 0. Clear? Now what we are going to do is, I am going to provide current. I am not writing current as I because there is intensity of magnetization I written over here. So I am going to increase the current in clockwise direction. So when I increases, right, now current increases, magnetic field increases. When magnetic field increases, the intensity of that magnetic field also increases. When intensity of magnetic field increases, the magnetization of this object also increases. So see, so I can say H increased, I increased. This is the second point or second condition. So now I have to plot the graph like this, right? So see, when H increased, I increased. But after it reaches a point, say A, even if I increase the current in the clockwise direction itself, the magnetic field also increases, hence the intensity increases, but further magnetization of that object is not happening. That is, all the domains now has been arranged in the particular direction. No more domains has to be rearranged. So now this object is completely magnetized. That means A is the saturation point. Now the saturation has reached. It is H is maximum or increased way and I is maximum. Right, at that point A is known as saturation point. No more further magnetization of this ferromagnetic object is possible. Right, that is, all the dipoles are now arranged. So now there is no other way. Even if I increase the current, is not going to change much. So what should I do? I am going to decrease the current. Right, initially it was 5 ampere, now it is 4, 3, like that. I am going to decrease the current. So decreasing the current means the magnetic field which was at the maximum point also goes decreasing. Similarly, the intensity also decreases, right? So that means H is going to be decreased. So you will feel that, okay, H is decreased means this plot has to come back like this, right? But it was found that no, it is not happening like that. The curve, when the values were plotted, the curve becomes like this. That is, when the current was decreased, that is, when the current was decreased, magnetic field decreased, and intensity of magnetization decreased such a way that H now became 0. Why? When current is decreased to the point 0, magnetic field is also decreased to point 0, then H is becoming 0. But it was noted that when H became 0, intensity of magnetization is not equal to 0. Right? That is, if an intensity of magnetization not equal to 0 means the object is still retaining its magnetic field even if the magnetic field application is 0. Now there is no magnetic field applied. We had applied a maximum magnetic field. Almost all the dipoles in the domain has arranged in a particular direction. Now I decrease the current, so that means the magnetic field decrease. When the magnetic field decreases, intensity of magnetization also decrease. But at the point when the current is 0 and magnetic field is 0 and intensity of magnetization is 0, but magnetization of the material is not completely lost, or I can say the magnetic field or magnetic nature of that object is still retained, right? So this point, let's say B, this OB, right, is an area where H is 0, right? H is 0, but I is not 0. That point or that region BO is known as retentivity. What is called? Retentivity. That is the region where the object, the ferromagnetic object, is retaining its magnetic property even if the application of magnetic field is over. Clear? Now, capacity of the substance to retain this magnetism even when the magnetic force is removed is known as retentivity. Clear? Now, if the retentivity is as much as higher, that much it is a good magnet, right? Now, as the retentivity is less, that much bad the magnetic is. Right? That means when you remove the magnetic field, that doesn't act like a magnet. Now what we are going to do, half the portion is completed. Now we are going to do is, now the current is reached 0, right? Now where can I increase from? See, initially it was increase the current from 0. It reached 5 ampere. I decreased from 5 to 0 again. Now I will see, this was a number line like this. It from 0 to 5, then 5 to 0. Now I go in this direction, that is negative direction. Negative direction means current was in clockwise direction. Now I will increase the current in anti-clockwise direction. Right? Now current is in anti-clockwise direction. Now current, when it is anti-clockwise direction, that means magnetic field will be also in opposite direction, right? So initially suppose magnetic field was increased from 0, 1, 2, 3 like that. Now the magnetic field will be from what? Increasing itself but in negative way. Direction will be opposite. So it will be 0, minus 1, minus 2, minus 3 like that. So magnetic field also increases in opposite direction or the reverse direction. So if magnetic field is negative, let's say negative itself, in what? High values, it is going on increasing in negative values. Similarly, H will be also increasing in negative values, right? H is, that means intensity of magnetization increases in negative direction. Then at some negative H value, right? Some negative H value, the magnetization, or I can say intensity of magnetization, was found to be 0. See, initially still the magnet is magnetized, right? So I increased the current in opposite direction. So magnetic field was induced in negative direction because it's an anti-clockwise direction. So H, that is intensity of magnetization, initially it was 0, 1, 2, 3, 5. Now then I decreased from 5 to 0. Now I am moving from 0 to minus 1, minus 2 like that. So I am increasing the intensity of magnetization, and it was found at some negative H value, the I, that is now the material has lost its entire magnetic property. Or I can say now the object or the magnetic material or the ferromagnetic material has been demagnetized, right? So let's say that point, let's mark it as this point. See, at that point H is negative but I is 0, right? So let's plot it like this. Okay. Oh shit. That means at point C, let's say like this point C, now this material is having I is equal to 0 but H value is there, right? That means I is equal to 0 means the object has lost its entire magnetic property, right? Or I can say now the dipoles are in random arrangement, right? So this OC, that is OC portion, is called coercivity. What is called coercivity? Right, coercivity means that is how much more negative H is needed, right? How much minus intensity of magnetization is needed so that the object becomes demagnetized, right? How much H is needed so that the object becomes demagnetized. That is known as coercivity. Clear? Right. So how much this, see, how much this much coercivity increases, that much good the object is the magnet is. When coercivity is less means only less negative values required so that it becomes demagnetized. I am telling you, if this much value, see, if H is say increased in a value, say it is -5 and there is a just H value as -3. So if I am increasing in negative value and -3 has reached, suddenly that object is now having 0 magnetization. So that means it has lost its magnetic property. Another object I can still push to -5 value. Then only it becomes demagnetized. So which object is good? This one, right? So when H value, right? So that means this value is increased. The -5 will be here, right? So -3 will be here. So which is good? So as much the coercivity increases, that much good magnet it is. Similarly, how much increasing the retentivity is, that much good the material as a magnet is. Clear? I'm just adding it, guys. Now, what happens if the current is increased? Now, if this current is further increased, right? We are increasing it so that H has reached a negative value, I has become 0. Now, further, I have increased the current in opposite direction. H is negative. I now from 0, it will move in a I means intense magnetization. Now it moves from 0 to which value? Negative values, right? So now I is negative values going on increasing. That is, the dipoles are now getting slightly arranged in a particular. Initially the dipoles were arranged in this direction. Now the dipoles are arranging in this direction, right? Opposite direction, and they are getting a common direction, right? Initially random, so I became 0. Then I am increasing the current, magnetization increased. So initially means in this positive section, all the dipoles were arranged in this direction. Now in the negative direction, obviously they will be arranging in the opposite direction, right? And they are all aligned, and at some point, at some its negative value, right? High negative value, now I has reached negative high value, right? Maximum magnetization is over. All the dipoles have been now arranged in this direction. Now no more alignment can be done. That means a saturation has now reached. Let's say that point is D, right? D is that saturation level, right? Now even if I increase the current in anti-clockwise direction, which has been remained so, magnetic field is increasing, H is increasing, no further I increase in the negative direction, right? No more dipoles to be arranged. So I can say saturation is increased or reached. Now we have this current which is in anti-clockwise direction. I am going to decrease that current. So again, obviously the magnetic field is going to happen was, it is going to decrease, means now H was -5, right? Now H is going to be decreased, means what? It becomes -4, -3 like that. See, H is going on decreasing like this, right? So what happens? H is going to be decreased in the negative value direction, or negative value itself. Now current is also going to be decreasing. Right, current decreases, magnetic field decreases, H decreases. Similarly, magnetization also decreases. At some point, when the current is 0, H also becomes 0. Right, but again, retaining of magnetic field. That means all the dipoles have not become random motion. So that means they are still retaining magnetic field at some point. Let's say that is this point. So at some point where we have reached that current is 0, H is 0, still I is not 0 in the negative region. That means this is OB. Let's say this one as let's say E. Then OE is also a retentivity region. That means there is still magnetism retained. Now this one direction is very easy, guys. Now again we are going to, now current has reached 0, right? So current is anti-clockwise direction, current now is 0. Further I am going to increase current in which direction? Clockwise direction. Again magnetism increases in positive value, H increases in positive value, current increases, right? Similarly, intensity of magnetization increases. Right, like just like this one. And at some point, I has reached a maximum value. Further increase in current and magnetization doesn't have any effect. Then it reaches a point A. Then this curve completes again and again. This loop is known as what? It's called as hysteresis loop, right? From magnetization to demagnetization, from magnetization to again demagnetization. This loop is known as hysteresis loop. This much clear, right? Now we as can see, I is always lagging behind H, right? H always first reaches 0, then also I is not equal to 0, right? So I can always say intensity of magnetization is always lagging behind H, or applied magnetic field's intensity. In the case of paramagnetic field, see, in the case of dia, let's say above dia, if I take one H value, right, one H value, I plotted a straight line like this. How many I values are there? There is 1, there is 2, and there is 3. So for particular value of H, there are multiple values of I. That is the case of what? Diamagnetic object. But in the case of paramagnetic object, it was directly like this, right? I is proportional to, or I is equal to chi into H. So one value of H only has one value of I. Whereas in the case of paramagnetic object, if it is like this, ferromagnetic object has multiple values for one value of H. One H value has multiple I. Clear? Whereas now, guys, in the NCERT textbook, this I has been just replaced by B, because B and I are quite similar. B means the object has been a magnet, net magnetic field. Remember, B net was equal to mu into I plus H, right? So in place of I, you just wrote B. It's quite similar. Or if you don't remember, B naught is equal to mu naught into I or H, right? Clear? This was a relationship between B and H, right? So from here also we find some relationship between B and H. Here from here we can find B and I. So in place of I, they are just retaining it to, or replacing the value of I with B. The graph is same, ditto. Clear? Now the last section which we have to deal with this chapter is how to look at the hysteresis loop, and can we know whether it is a permanent magnet or a temporary magnet. See, if the area of the hysteresis loop is narrow, small, slim, right? It is a what? That much less coercivity and retentivity, right? So that means it is having less area. Less area means less energy loss. Right? Area of a hysteresis loop gives you the idea how much energy is lost during the entire cycle of magnetizing, demagnetization, etc. Right? Magnetization, demagnetization, then again magnetization, and then demagnetization again comes back to magnetization. This is how the loop is. So the area which is or the hysteresis loop gives you how much energy is lost during that cycle. So a permanent magnet will have higher retentivity. How much retaining it is, magnetism is retained in it. Coercivity means how much energy is required to demagnetize it. Right? That much energy is required to demagnetize it means it is a very good what? Permanent magnet. right? And similarly, large area of hysteresis loop means that much energy loss, right? Energy loss means that much increase in magnetization, then that much increase in demagnetization. So the energy loss would be higher. So if an area is having these three quantities higher, means obviously that loop has to be looking very broad, right? So that means by looking at a broad magnetic hysteresis loop, I can say that magnet or that hysteresis loop is of a permanent magnet, whereas the narrow loop indicates that what its coercivity is less, retentivity is less, its energy loss is very less. That means the cycle goes off like this and it completes like this, right? I hope you understood. So the temporary magnet, which is the case of generator, transformer, etc., where induction is happening, they are having what? Temporary magnetic property, means they are, there is an example is that of soft iron. Soft iron is having narrow magnetic hysteresis loop, whereas the steel will have the hysteresis loop very large. Clear? Okay guys, we are finishing off today's chapter. Not today's chapter, the entire chapter is finished. Please go through the notes which you have written or writing along with the class videos. Okay, bye.